All right, in this example, we look at a line integral of vector field again, but we make some interesting observations about these line integrals. All right, so what we can see here is that we have 2 points, P and Q. All right, and there are a variety of different ways to get from the point P to the point Q. We can move along this straight line, path C1, or we can take this sort of like parabolic path up to from P to Q, or we can go from P to Q along this straight line in the XY plane, and then we can come straight up to the point Q, so kind of along the edges of a triangle. Okay, so the point that we're seeing here is that to get from P to Q, there are a lot of different paths we can take. We can take a straight line, we can take a curvy line, or we can take this straight line. So we have several different ways to get from P to Q. And the question is, how does the line integral or the work integral behave? Okay, so as we look at a line integral of a vector field along a path C, right, we can see that there's the line integral along the path C1, so just one arc of the path, or we can do this line integral along the path C2, or we can find the line integral from P to Q. All right, so this curve C is just going from P to Q, right? We can split along C3 and C4, we can do the integral in 2 pieces. So the integral along the curve splits up into the line integral along the path C1, and then you add the line integral along the path C4. Okay, and the question is, what happens to these values? Are they all the same? Okay. Is the line integral the same value along all of those different paths from P to Q? And we will kind of see what happens in this particular example. Okay, so the vector field, okay, that we're looking at, this is a 3-dimensional vector field. We're not seeing it in this picture. There's some sort of vector field drawn here, okay, given by this formula. So f of x, y, z, the vector field is xy, yz, xz. Okay, so let's just kind of look at the first along the path C1 first. Okay, that is the line. Okay, so C1, if you parameterize it, is going to be the line that goes from 0, 0, 0 to 1, 1, 1. So that'll be t, comma, t, comma, t is the parametric form of that line, and time goes from 0 to 1. Okay, so if we were going to set up the line integral along this path, okay, we would have to integrate from 0 to 1. Okay, we would have the vector field along that curve, so x and y and z are all t, so we'll get t squared, t squared, t squared for the vector field along the curve. Okay, then we will dot product with the direction vector of that line, which is 1, 1, 1, or the r prime at t, and then we will need to do a dt integral. Okay, so I think we can see here that when you do that dot product out, you'll get the integral from 0 to 1 of 3t squared dt, and the answer to that is t cubed over 3 times 3, which is just t cubed. T cubed from 0 to 1 is just equal to 1/3. So that is the value that we get along the path C1 for the amount of work, the work along the path C1. Okay, if we look at the path C2, we can see here that they've been kind enough to provide us with the equation, the parametric form of that path. Okay, so we'll go ahead and try to do that integral also. Okay, so let me create some room here. and we're wondering if this value is going to be the same as the work along the path C1. Okay, so because the curve C2 was given to us, it was given us in parametric form as t comma t squared comma t to the fourth. We know that r prime of t is 1, 2t, 4t cubed. Okay, we know the vector field along the curve is x is equal to t, y is equal to t squared, so that would be t cubed. Y times z is t to the sixth. X times z is equal to t to the fifth. Okay. So when we do the integral along the path C2, f dotted with dr, okay, we will get the integral from, let's see, we need to go from 0, 0, 0 along the path C2, so that means that time t had to be 0. And if we want to end up at the point 1, 1, 1, t also has to go to 1. Okay, and what we're seeing here is that r of 0 with this curve is 0, 0, 0, and r of 1 at time t equal 1 is 1, 1, 1. And so because that was the point P and the point Q, we have the correct time values now. So if we take the vector field along the curve and dot product it with the direction vector of the line, we'll get t cubed plus 2t to the seventh plus 4t to the eighth, okay, and dt. And let's just go ahead, and that should be a nice easy integral to work out. Let's go ahead and evaluate that integral. So we'll get t to the fourth over 4 plus 2t to the eighth over 8 plus 4t to the ninth over 9. Evaluating from 0 to 1, so that'd be 1/4 plus 2 eighths plus 4 ninths, okay, which, I don't know, 1/4. I'm pretty sure that that is not equal to 4 ninths, 17 over 18, okay, which does not equal to a third. So one thing that we're finding is that the work along this particular arced path versus the straight line path, the work was a third, and then the work along this other edge is equal to 17 over 18, more work. Okay, so we've discovered something very important in this problem, that the line integrals, okay, line integrals are generally what is called path dependent. The amount of work depends, the amount of work it takes to move along a path depends on the path itself, okay? And that is because the vector field could be doing very different things in different parts of space. So for example, you can imagine, like, if the force field is a wind field, for example, and you're trying to walk up the hill along these straight line paths, that, you know, the wind may be hitting you in the face here, so you're having to do maybe a lot of work, right? But here, the wind along this other path, you know, may be kind of behind you, right? So just based on the nature of the path itself, the vector field could be doing something very different, and, you know, the wind could actually be helping you up the hill. So that is just a general idea about why you definitely expect line integrals to be path dependent in general. Okay, I will leave it for you to compute. So you should try to compute the integral of f dotted with dr along the path C from P to Q by computing along the path C3 and then adding that to the work done along the path C4. So the line integral from P to Q along the edges of the triangle will require you to compute the work along one path, the work along the other, and then you get to add those two results together. And I think you will find that the answer will most likely be different from 1/3 or 17/18. You might get something very different as an answer.